Welcome to This Explainer. Today, we're decoding what I like to call an engineering superpower, scientific notation in orders of magnitude. We are going to show you exactly how professionals navigate the absolute extremes of the physical universe, from the unimaginably massive right down to the infinitesimally small. Because, as you'll see, understanding scale is the true secret to engineering.
Let's just jump right in. Have you ever thought about the sheer mind-numbing frustration of tracking dozens of zeros when you're measuring the universe? I mean, if you're an engineer calculating orbital trajectories or a physicist measuring atomic structures, writing out standard decimal numbers quickly becomes a total nightmare. So we really have to ask ourselves, isn't there a better, more efficient way to write these extremes?
Consider this comparison, because it absolutely hits the nail on the head. On one hand, you've got the distance from the Earth to the Sun. We're talking 149,600,000,000 meters. That is a lot of space taken up just by zeros. And on the other hand, the mass of an electron, it starts with a zero, a decimal point, and then 30 consecutive zeros before we finally hit the digits 911. Writing that gigantic distance next to that microscopic mass is visually overwhelming, and honestly, it's incredibly prone to mistakes. Imagine dropping just one of those 30 zeros in a critical calculation. There absolutely has to be a better way. Well, thankfully, we have an elegant solution to this whole tyranny of zeros. Scientists and engineers use scientific notation and orders of magnitude as a highly precise lens to view reality. It's a convenient, meaningful system designed to describe both the incredibly massive and the insanely small. It gives us a reliable, standardized shorthand, completely cutting out the clutter.
So how does it actually work? Converting a clunky standard number into this clean formula is literally just a two-step process. First, you write a base number, let's just call it A, that sits comfortably between 1 and 10. Second, you multiply it by 10 to the power of n. And that little n is basically your instruction manual. It tells you exactly how many times to multiply or divide by 10. So 3,000, that becomes a crisp 3 times 10 to the power of 3. And 0.005 shrinks down neatly to 5 times 10 to the negative 3. Simple, right?
I love to think of powers of 10 as a kind of universal decoder ring. Notice how the positive powers represent the large numbers. 10 to the power of 1 is 10, jumping all the way up to 10 to the power of 9, which is 1 billion. On the flip side, the negative powers represent the microscopic world. 10 to the negative 9 is 1 billionth. Every single step up or down corresponds to a clean, predictable factor of 10, building a perfect ladder of scale.
And because these specific powers pop up all the time, engineers came up with a universal vocabulary, unit prefixes. Instead of saying 10 to the power of 6 hertz, an engineer just says mega. Converting 1 million hertz to 1 megahertz is entirely effortless. A kilometer is just 10 to the 3 meters. A nanosecond, 10 to the negative 9 seconds. It literally takes complicated math and turns it into intuitive, everyday engineering language.
Here's the real kicker, though. Engineers are often way more interested in the order of magnitude, the general scale of a quantity, than its exact down to the decimal value. Take distances like 1,200, 3,400, or 8,700 meters. For a quick mental calculation, an engineer immediately recognizes these are all roughly on the order of 10 to the 3 meters. The exact same goes for time. 5, 30, and 100 nanoseconds are all grouped on the order of 10 to the negative 8 seconds. This lets them rapidly estimate if an answer is reasonable without getting bogged down in the weeds.
Section 1. Navigating space and time. Let's see how this actually plays out in high-stakes space and satellite navigation. Take space engineers. They routinely bounce between wildly different scales, and they use this exact shorthand to navigate those extremes. Compare a low Earth orbit altitude of about 400 kilometers, that's 4 times 10 to the 5th meters, to the massive 384,400 kilometer jump to the moon. That's 3.84 times 10 to the 8th meters. By just glancing at those exponents, the 5 versus the 8, an engineer instantly grasps the huge leap in scale.
Then we have this absolute powerhouse of a number, the ultimate speed limit of the universe. The speed of light is roughly 300,000 kilometers per second, but written in our engineering notation, it's cleanly compressed into a single, highly manageable expression, 3 times 10 to the 8 meters per second. This constant is foundational to physics, and framing it this way makes it incredibly easy to plug into complex equations.
But hey, it's not just deep space that relies on this. Global Navigation Satellite Systems, or GNSS, handles some crazy scale shifts right within the exact same system. Just think about the contrast here. The GPS L1 frequency operates in the billions of hertz. Specifically, 1.57542 times 10 to the 9th hertz. But the actual physical signal beaming down to your phone, that drops right down to 1.9 times 10 to the -1 meters. That is just 19 centimeters. And speaking of navigation, let's look at positioning accuracy to see why these scales matter to us. Your standard single-point accuracy, that gives you about a 3-meter error radius. But advanced RTK, or real-time kinematic positioning, shrinks that error margin down dramatically to 2 times 10 to the -2 meters, which is just 2 centimeters. Scientific notation beautifully highlights this massive leap in precision. Which brings us to a pretty dramatic question about timing accuracy in these systems. A nanosecond. 10 to the -9 seconds. To most of us, that sounds, well, totally insignificant. It's literally 1/1000th of a second. But what actually happens when a GNSS satellite clock is off by just that tiny, imperceptible amount? What does a 1 nanosecond timing error actually mean in the real world?
Astonishingly, that microscopic, almost non-existent fraction of a second translates to about 30 centimeters of physical ranging error right down here on the ground. Think about that. A 1/1000th of a second mistake means your navigation is suddenly a foot off target. This definitively proves that dropping a zero or slightly misunderstanding a decimal place can have very tangible, real-world consequences.
All right, moving on to Section 2, the engineering mindset. We've seen the extremes of the universe. Now let's explore how this mathematical shorthand actually rewrites the way professionals think.
Because the truth is, you don't always need exact numbers to grasp the physical significance of something. Say you need to estimate the momentum of a spacecraft with a mass of 500 kilograms traveling at 7,700 meters per second. Instead of doing exact long multiplication on a notepad, an engineer instantly estimates its momentum just by multiplying the magnitudes. They quickly calculate that it's roughly 4 times 10 to the 6 kilogram meters per second. It's rapid, mental math relying entirely on an intuition for scale.
And this mindset is, frankly, absolutely critical. Thinking in orders of magnitude is what lets professionals make quick estimates, double-check if their calculated answers are even in the right ballpark, and detect mistakes early on. Honestly, many epic engineering failures throughout history haven't come from complicated calculus errors. They happen because someone misunderstood the scales and the units. Baking this intuition into your thought process serves as a vital safety net.
So, as we wrap up this explainer, let's hit those key takeaways. Scientific notation is your best friend for compactly representing extremes. It handles the massive and the microscopic with ease. Powers of 10 describe the scale, while those handy unit prefixes simplify our communication. And most importantly, estimation and true physical intuition will always beat simply memorizing exact values. Experienced engineers naturally think in these powers of 10 to spot errors, make rapid estimates, and truly understand complex systems.
Ultimately, this isn't just some convenient way to write numbers on a whiteboard. It is a profound way of looking at reality. Like this quote perfectly captures, engineers do not merely calculate numbers, they understand their scale. So the next time you look at a massive suspension bridge or rely on that incredibly precise GPS in your pocket, remember the hidden language of scale that makes it all possible. It really makes you wonder, what other invisible scales are silently governing the physical world around you right now? Thanks for tuning in to this explainer.